Hello and good afternoon, everyone. Thank you for joining us today. So the topic for today's webinar is techniques for analyzing obfuscated Android applications. So before we start with the webinar, let me introduce myself. My name is Vignesh and I work as a security researcher here at Appknox. I mostly focus on Android application security research, and I have been working as a penetration tester for over 3 years now. So yeah, let's begin with our webinar. So the agenda for the webinar today is firstly understanding what is code obfuscation. Why do application owners prefer to obfuscate their apps? Like what are the techniques which we usually see, uh, code obfuscation techniques we usually see in Android application? Then we will, in the lab session, we will go through few examples like how the obfuscated code looks and how a non-obfuscated code looks. So we'll have a comparison of that. Sorry. Next, we'll try to use tools like Frida and Jadx to analyze the obfuscated Java application. Then we will see how we can analyze an obfuscated native code library for Android. And finally, we will look at a React application which is shipped with Hermes bytecode. Okay. Okay. So let's start with first understanding what is code obfuscation. So basically, code obfuscation is a technique of obscuring the application logic or business logic. So it becomes difficult for the reverse engineers or anyone who is trying to decompile the application and and trying to have a look at the code. It becomes difficult for them to understand. It becomes difficult for them to understand the application logic and everything. So security researchers, basically, if the code is obfuscated, we face difficulties in understanding the business logic. Or even if you're running the application through a vulnerability scanner, it becomes very difficult for the scanner to actually follow the flow of the application to find the vulnerabilities. Why app owners need to obfuscate their apps? So mobile applications, mostly Android based applications, are usually written in Java or Kotlin. So once an application is shipped, basically it is shipped as a Java text code, which can be easily reverse engineered to the Java code using tools like Jadx and all. So basically, it is very easy for an attacker or anyone who wants to have a look at the code to just throw the Android app APK in Jadx and look at the code. So basically, this will allow stealing of intellectual property. So if if a third party is able to understand the logic of the application logic, they can recreate it in their own application and basically create a clone application. It becomes possible to extract information and harvest credentials. If the application is having any hard coded APIs or secrets, they could be easily extracted through the app. It becomes again very easy to identify vulnerabilities. So it becomes easy to go through the code manually or through a source code analysis tool, and it will just list out all the vulnerabilities the application has. It becomes, once the application logic is understood, it becomes very easy to tamper with the application and inject malicious code. So one example of this could be basically tampering the application to access its premium features and then repackaging the app. So a lot of such applications are available outside of the Play Store. So let's try to understand few of the code obfuscation techniques which we usually see or come across in Android applications. So first is renaming classes, fields and method libraries, transforming arithmetic and logical expressions, encryption of strings, classes, removing certain metadata from the application, and hiding calls to sensitive APIs. So we'll just go through each of the technique once individually. So first is renaming the class names, field names, method names, and etc. So on the left, you can see this is what the original source code looks like. You can pretty clearly see the function names, the variable names, etc. This is what the on the right side, this is what the obfuscated code looks like, where the function names and all is are being obfuscated. So you can see just on the left side, just by reading at the function name, you are able to have an idea like what the function would be doing. While on the right side, this becomes very difficult. You will need to go through each line of the code to understand what the function is actually doing. Next technique is transforming arithmetic and logical expressions. So again, on the left side, you can see in the original program, here res is equal to x plus y, and uh, basically whatever the value of x plus y is returned. So you can just understand that this function is performing an addition operation. On the right hand side, again, the function is same. The operation performed by the function is also same. But you cannot just understand what the function is doing just by looking at the source code. Next technique is encryption of strings and classes. Here, on the left, again in the original source code, the message.display is printing your account number is invalid. On the right, again, message.display is printing a message, but here the string is obfuscated. So you don't exactly know what the message is being printed. If you have been reverse engineering applications, like one of the common techniques is to like just look for strings, then see what are the references to that strings, and then try to understand the logic of the function from there on. So if the strings are obfuscated, this technique becomes pretty much useless then. Coming to the next one is control flow obfuscation. So on the left, again in the original source code, you can see like there's a function compare to. In that, there's one if statement which tries to compare if n is equal to 0. And based on that comparison, it returns. On the right side, where the control flow is obfuscated, again, like the operation is pretty much same, but it is very difficult to understand like where the comparison is happening, where the code is jumping to. So yeah, as you could see, like while dealing with obfuscated apps from a pen testing perspective, there are a few challenges that are usually obviously one will face, which is reduce code reliability. So as we saw in previous examples, by looking at the code, it becomes very difficult to understand what the application is doing exactly. Since the code readability is quite low, it becomes difficult to identify vulnerabilities just by going through the source code. Few of the static analysis vulnerabilities that could be easily found just by going through the source code in an obfuscated apps, finding the same vulnerabilities becomes pretty much difficult. Slower analysis and testing progress. So again, like to understand the application logic, you need to dynamically analyze the code, which will just slow down the testing process. Okay. So this was the theory part. We'll jump to the labs now. So I hope that you're able to see the screen of the Android device here. So we have a sample application that we have prepared for this webinar. So it is a simple login app where the user is prompted to enter the username and password. And then there's a login button. So we'll try to enter some random characters and you'll get a wrong credential. So firstly, we have opened the same app, the deobfuscated version of this application in Jadx. So we'll just try to go through it. So if you go to resources and Android manifest file, you can see there are two activities. One is dashboard, and this is the main activity, WebViewLab.main activity. So if we try to open the source code of this main activity, you can see this is what we get. So we have gone through like the different techniques of obfuscation. Will someone be able to tell me like what obfuscation technique could be used here? Nikita, can you help me with the answers? Okay. Uh, if you have guessed control flow obfuscation, then that is one technique which is being used here. Another thing that is the application is using is string obfuscation. So you can see it is using a deobfuscator with get string to actually receive the strings of the application. So we'll try to analyze this app and see if there are any hard-coded secrets in this application that would help us to log in into the application. Okay. So we'll be using the debugger inside Jadx. So firstly, we'll configure the same. On the Android side, basically this application is debuggable. So in the manifest file, you can verify the same thing. Here the Android debuggable is set to true. If the application is not debuggable, one thing you can do is like decompile the app using APK tools, then open the Android manifest file, and then just add this tag Android debuggable set to true, and then just recompile the application. If the app does not have a tamper detection, this will work pretty much. Okay. So few settings we need to do from the Android side. You need to go to settings and then developer options. You need to set wait for debugger to true, and then you need to select the app. So here the application is WebView Lab. Okay. So now if we try to launch the app, you will get this screen basically waiting for debugger. Now from here, you can basically choose which application you want to debug. This is the app we have, com.example.webview lab. If we double click on it, it will open the debugger view. Okay. So here in the code, you can see like it is the application is using a switch condition, and based on that, it is jumping to the code flow. So if you have been working on the Android AP case, one thing you will be able to understand is the basically the control flow of an Android activity starts with on create. Inside that, the first statement is always super dot on create bundle, and then set context view is there, which basically sets the layout for that activity. So what we can do is we can try to set up a breakpoint at the switch statement and try to understand what all cases it is going through. So yeah, this is our switch statement. So we can click on this left side. This will set the breakpoints for us. I can hit the play button. So this is the first breakpoint that Jadx has set for us, which is on the on create function. We'll again hit the play button. And this is where it has come to our breakpoint. So we can see like the value, the switch statement is using the value in V1 in deciding where to jump. So here we can see like the value in V1 is this. So we'll just copy this value for now. And we will just put it in a text file. And we can move ahead. Doing this again, we are trying to understand what is the control flow of the application. So if we go back to the code part, we will see the first case is ending in 8623. You can search here 8623. So we can understand like this will be the code that would be run first. The second case is ending with 6225. So this will be the second code statement, and this is how we'll be proceeding. Again, the third one is ending in 788. Next one is ending in 756. After that, the next one is ending in 696. The next one is ending in 450. The next one is ending in 394. This is ending in 075. This is ending in 728. And this is it. Like we have exhausted the control flow. So now we can go to the code part and we can try to reconstruct the code. So the first one was ending at 8623. So this, we can skip the break statement. We can just take this string part and paste it here. The next one is ending in 6225. Similarly, we can just take the strings statement and paste it here. I am skipping the break statement because basically it's part of the switch. It tells the switch to basically end the control flow here and again go to the switch statement. Next one is ending in 788. So this is our super dot on create. The next one is ending in 274. So here is the stat context view code. Here a v1 variable is created and it is linked to the button layout ID button. To 9. Similarly, again a ed1 variable is created and it is linked to edit text layout 626. Again, another ed2 variable is created and it is linked to the edit text to layout ID. So these are the two edit texts. This is the button. Again, this is the second button. This is the case. Here basically for the B1 button, it is setting a set on click listener. And if that button is being clicked on click, this code will run. We'll just copy the whole thing and paste it in our text file. Till the break statement. We can clean this up a little, but on click, we can see again there's a switch statement and again the similar logic is being used. So using the same method of like setting the breakpoint on the switch statement go to instruction, we can try to recreate the original source code of the application. So for the first on create function we somewhat did. Similarly, we can do it for the next part also. Just to save time, we have done it already. So this is what the somewhat the source code will look like. So here is our set on click listener. Inside that, once it's clicked, this is the code that we have. So it will take the value from our first edit text and it will try to compare it to a string. If the comparison is not successful, we'll get some message. If the comparison is successful, it will retrieve the value from the second edit text. Again, it will try to compare. And if that comparison is not successful, we will get another toast. And if it is successful, it will go to this dashboard activity. So we can like based on this, we could like make a guess that this is the login logic of the application. So the next step is we need to understand like what is the string values it is comparing to. So that will be our like username and password. So we need to get these strings next. We'll try to get a fresh debugger session. Okay. So here we can see like the app is using some deobfuscator app debug and it is using the get string function of this class to retrieve the actual string. Here again. So we will just go to the get string function and see what it is doing. So it has a string array and it is returning this. So here is our get string function and it is returning a string value. So what we can do is again, we can set a breakpoint here on the return of the return value of get string. Yeah. So I'll just reset the breakpoint and then we'll run the application. Yeah, this is the Android window here. So the first breakpoint is again set on the on create function. We can just continue here. We have come to the login screen. We can enter some random value. We'll click on login. And here in the code, we can see like we are inside the get string function. This function is returning v3. So we can see what is the value in v3. This is the value of Appknox at the rate 123. If we proceed ahead, we are getting the wrong credential. The string is wrong credentials. If we proceed ahead, this is the toast message that we receive. So in the first edit text, we can try with the Appknox at the rate 123 value. We'll try to log in again. Okay, Appknox @ 123. This is the value we got as return. The second time, the value which we are getting is this web view webinar lab 2023. So we'll just copy this value in the text file again. So this will be our password most probably. If we continue ahead, we are getting the wrong credential. If we again continue, the same message we will get in the app. Okay. So let's try with this password now. Let's click on login. Again, in the Jadx debugger, the first value we get is Appknox @ 123. The second is this password. Now we are getting a redirecting to something as a string, and we'll pass this. And you can see in the Android app that we have successfully been able to log in and we get a flag value. So this whole similarly, as we tried to solve this challenge using the Jadx debugger, we can also solve this using Frida. So instead of going through this get string function using Jadx debugger, we can hook it using Frida and then try to get the return value of this function. So those who are not aware with Frida, Frida is a dynamic instrumentation tool which basically allows us to hook into functions or read the memory of the application and also modify the return values or the parameters for this. Okay, we don't need Jadx now, so we'll just close it. On the Android side, we'll close the debugger. Again, we can go to developer options. Here we'll disable wait for debugger. Yeah. So now you can see like the application didn't wait for a debugger to connect, it just launched directly. So this is a small Frida script which we have written. So we'll just go through it. The first line basically java.perform tells basically whenever the Frida script is connected to the application, this code needs to be executed. So the second line, java.enumerate loaded classes. So basically this will enumerate or list down all the classes that are loaded by the application. The on match function, here we can like try to match a particular class which is being loaded. And this will just print console.log is just printing the class name. And the on complete part just tells what needs to be done while exiting this enumerate loaded classes function. After that, we have created a let deobfuscate a helper variable. And in that, we are creating an instance of this deobfuscator.java. This is the class that we saw in Jadx. So for the deobfuscator helper class, what we are interested is the get string function. So dot implement. So basically what we are trying to do is modify the implementation of the function in memory. So whenever the getString function of the deobfuscator helper class will be called while a script is running, it will log this statement like getString is called. Here, this will get us the return value of the function, which is what we are interested in. And then we are using the console log statement to just log that return value on our terminal. So let's try to run the application using this script. List packages. So the PM list packages will list all the package names that are installed in the Android device. And we know that the package name that we are interested has something WebView inside it. So we'll just search for that. This is the package name of our lab application. So to spawn this application using Frida, the command is Frida -u, which basically tells it to connect over USB. F, it tells it to spawn. This is the package name. -L tells what script we want to run along with this. So we want to here run the Frida script that we just saw. Okay. I'll just minimize my terminal window a little. So like the Android screen is also visible. Now we can run the Frida command. Okay, it failed to attach. We need to initialize the Frida server first. So my Frida server is inside data/local/temp folder. So yeah, now I've initialized the Frida server using this command. Now I'll try to spawn the application using Frida. We need to disable this wait for debugger. Let's try again. Okay. Here we are on the login screen. We can just copy paste Frida snippets also using the Frida REPL. We'll just do that here. So here is a script to get the return value of the getString function. So let's try to enter some random username and password. So yeah, here we can see the getString return value is Appknox @ and the second return value is wrong credentials. So we got our username. Let's try to log in again. So here's our password also now. Yep. We'll are able to log into the application and get the flag. So this was a lab to demonstrate like how to deal with obfuscated Java code. Next up, we'll be seeing an example where the native library is being obfuscated. Okay, so here is an app debug.apk that we have. So we have just decompiled the application using apk tool. The command for that is apk tool t and app debug.apk. Since we have already done this, I won't be running this command again. We'll just go inside the app debug folder. You can see like this all we got after decompile the apk. So we'll go inside the lib folder and then ARM64, which is the architecture of our Android device. If we do ls, we know we have this lib.keys.so file. So to analyze this file, we can open it in a disassembler of choice. Here I am using Binary Ninja. So you can see here it has like two JNI functions. One is main activity get API and another is main activity check root. So if we go inside the check root function, we can see the high level of the sudo C code. So we can see like here there's an array which has these values. Basically, then there's a for loop iterating through the array. Like each value of an array is passed in the transform function. The return from the transform function is then passed to the exist function. Okay. So again, like you can, based on the types of obfuscations we saw before, you can guess like this is a string encryption technique. So we can try to retrieve the original strings that are being passed to the exist function. So for that, we'll need to try to see the transform function. So yeah, this is the code for the transform function. Like we can go through statically analyzing each line of the code, or again, we can just use Frida to get the return value of this function. So we have a script already written for this. We'll just go through that script. So here, like there are two functions that are written and this set timeout. So basically what this tells is to run the get base address function after waiting for 200 milliseconds. So we'll try to see what the get base function address function does. So here it has one variable called offset, which has the value 820. So basically this is the function offset value. So if you again go to the disassembler, you can see like the transform function starts from 0A20. So this is the offset of the function. After that, we have another variable address, which is storing this module.base find base address. So basically this will return the base address of this libkeys function in memory. So at what, basically it will tell at what address in memory is the libkeys function loaded. We have another variable basically which adds the offset value to the base address. So this will exactly tell us like the memory address at which our get string function is there in the memory. Then there are two log statements which will basically log the base address and the function address. And then this intercept function method is called, which takes again like the function address and our base address. So let's go through the intercept function method. So inside that, the first line is intercept.attach. Intercept.attach.address. So basically this will try to attach to the function address. So this address contains the memory address of the function we want to hook, and this attach will attach the interceptor to that function. The on enter tells like what code we want to run once we enter the function. So we have a logger statement basically that tells that we intercepted the function call to this function, and second logger statement is what is the argument that is being passed to this function. And on leave, which is what we are interested in more since we want the return value of this. So on leave, we are logging the return value of the function, and then we are returning the same since the function expects a return value. So let's try to launch the application using this script. So yeah, on the one side we have the terminal window, on the other side the Android device. This is our script. So first we need to find the package name. So we'll use the pm list packages command. So this was the package we used for the first demo. This is for the current one. Okay. And you want to run the script.js. Okay, so we are getting this cannot read property add. So basically what's happening is here we are trying to add offset to the null value. So we are not able to find the base address of the library. This is usually because our script is running before the library is being loaded in the memory. So we can increase the timeout and try. So yeah, now it worked. So here we can see like the first argument to the get string to the transform function was this, and this is the decrypted string value. So yeah, here we are using Frida, we were able to find the original or decrypted string values. Like there's another method that we'll like to demonstrate for the same, which is finding the decrypted string values using emulation. So what for that we are going to be using the Quilling emulation framework. So basically this is a emulation framework that is built upon Unicorn. So this allows like cross-platform emulation. So on an x64 machine, you can emulate libraries or executables from different architecture like ARM64, MISPs and all. If you want to install Quilling, it can be done using a simple command pip install Quilling. This will install it. And you can find a documentation of the Quilling framework here, docs.quilling.io. So we have already seen like the native library in the debugger. So let's try to emulate it using Quilling now. So you have again like already written the code for this. We'll just go through it, go through the code once. So we are using the Python binding for Quilling here, but it has bindings in other languages too, like JS and C. So whichever you are comfortable, you can use that. So the first statement from Quilling import star. So basically we are importing all the constants and functions from Quilling. The second statement, Quilling.constants. We are specifically interested in these two constants. What are they and what they mean? Like we'll go through that later. Again, we are importing through OS constants like string, size, and pointer. These are basically the variable types. From Unicorn, we need two imports, which is the UC mem write and UC proc all. Basically, these are the permissions for the memory regions. And then we are importing the struct, which is native to Python. So we'll be starting from the main. Here we are calling this my sandbox function, which has two parameters. This is our libkeys.so file, and basically Quilling comes with few file systems to emulate the file system related operations. So here we are using the ARM64 Android file system. So we are telling Quilling to use this file system for the emulation purpose. So let's go inside the my sandbox function. It takes the two variables that we've gone through. The first one, okay, the first variable start address. This tells where we want to start the emulation from what address we need to start the emulation. So we can go through to the disassembler. And we can jump to this 0xb80 and just will go to the disassembly. Okay, so this is the memory address from where we want to start our emulation. So basically this is loading all the encrypted strings in memory. So this is where we will start. And the end address is, this will tell where we need to stop the emulation. So C08. So this is basically after the transform function is called. So we'll have the plain text strings. Here we are initializing the Quilling objects. So it takes three parameters: path, which is the path of the executable or library we want to emulate. The rootfs, basically the file, this will tell the file system to be used for emulation, which is ARM64 Android. Verbose, this is a constant QL verbose, which dot debug. So basically, this tells that we want the output in a debug format. Then we are trying to get the base address. So as in Frida, we are trying to find out where the libkeys.so file is loaded in memory. So ql.profile.get load address. This will return us the base address. Once we have the base address, we are calling this prepare for emulation function, which we have written. We are passing the quilling object and the base address to this. So inside the prepare for emulation, we are creating three memory regions to have basically the encrypted strings to be loaded in these memories to have the stack region. We are initializing these three memory regions. These are the permissions for the memory region. So proc all tells basically it will have read write executable access, and these are the tags for this memory region. So after initializing the three memory regions, we are setting the registers. So we are setting the stack pointer to the memory region that we had initialized previously. We are setting the x29 register to this memory address. We are setting the x9 register to here, and in x8 register we have the 0x0 value. So basically our program expects these values in these registers from this point. So basically these values were retrieved by using GDB and setting breakpoint here. After the prepare for emulation function, next up we are using the quilling hook address API. So basically this API tells like what operation needs to be performed when this address is being called. So 0x, we can go to the branch transform function. So in the branch transform function, we are just setting the program counter value to our transform function. So once the execution comes to this BDC, the transform function is called. So we need to basically take the execution of the program, give the execution of the program to the transform function. So we are doing the same using this method. We are changing the program counter value. Similarly, in the second hook address API call, we are trying to read the decrypted strings once this address is being reached. So we'll just see what does what the library does at this address in disassembler. So yeah, basically we are hooking at the return value of the transform function somewhere here. So the x0 register should contain the return value. So we'll try to retrieve the return value by uh, reading the value of the X0 register. So this way we are trying to retrieve the decrypted strings. And in the second hook address, like once the transform function is done executing, we again need to give the execution flow back to the main function. So here again, we are branching to the main function, where we are writing the piece return address to the inside the PC program counter variable. Then we are after this we are using the set API calls of quilling. So basically here it will intercept the printf libc function. Here the QL intercept on call tells that when the libc printf function is called, we need to perform this operation. The operation performed specified in the myprintf function. So we can go to the myprintf function. So it is just retrieving the two parameters passed to the printf function and trying to log it. So basically these are the wrappers that we are defined around the printf function, string length function, and string cat function. They perform the same operation as the libc variants of these does. This is so because quilling does not have the context of libc functions. So we need to try to emulate these functions. And at the end, the ql.run function tells quilling basically from what address to what address do we need to emulate the library. So we'll just try to run the script. So yeah, here we got our decrypted strings. Quilling also will log, since it is in debug mode, it will log all the memory read write operations. That's why you get this also. So here, like using both Frida method and quilling method, we don't have to manually examine the transform functions. We can skip that part and save some time during the analysis. Okay. The last part, what we wanted to demonstrate today is like the React applications. So usually React application is shipped with an index android.bundle file, which contains the source code of the application. So you can see like this is a normal React app. We have decompiled it using using APK tools. So we'll just go through it. Inside that, in the assets folder, you will find this Android index.android.bundle file. If you run the file command on this, it will say that it's an ASCII text file. You can actually analyze the code inside the index file just by loading it inside the normal HTML file. So if you basically see the code for text.xml file, that there's an HTML tag. Inside that, I've defined a script tag, which is basically loading this index.android.bundle file. So we can try to open this in Chrome. So we have started an HTTP server here. In a new tab, which is open this. Test.html file. Okay, we can use the developer tools of Chrome to go through the source code. So here we can see like the index.android.bundle file is being loaded. And this is basically the source code of the application. And you can use all the functionalities of the Chrome developer tools. You can set breakpoints and all to analyze it. So we'll just see the application itself. Again, like, sorry, this is a basic app which has a login page. It requires a username and password, and it has a login button. So we can search for login. Here you can see title login on press. It tries to compare it with these two values, Appknox and strong password. And if the comparison is not successful, it will alert us the invalid credentials. So we just got the username and password. I just loading the index.android.bundle file inside the developer tools. So we'll just see if these credentials work. Yep. And we are able to log in. Okay. So sometimes like the application is shipped with basically the JavaScript code is compiled into Hermes bytecode and the application is shipped with Hermes bytecode. So when that is the case, again you can decompile the application using APK tool. You can go to assets folder. Again, you will find this index.android.bundle file. But if you run the file command on it, you can see like the type of file is Hermes JavaScript bytecode version 84. So when this is the case, again, you can disassemble the Hermes bytecode using a tool called HPC tool. So it is available on GitHub. You can just like clone it from here and use it. So you can see it has two options, like one is disassemble, assemble. We can try disassembling the index.android.bundle file using this. Disassemble. And then we need to specify an output directory for this. Output 2. You can see it is trying to disassemble the Hermes bytecode. Completed. We will have the output in the output 2 folder. Okay. It has given us three files. One is strings.json, one is metadata.json, one is instructions.hasm. So we can see the instructions file and try to go through it. This will contain like the instructions of the code for the application. Yeah, you can see like this is much if the application is just shipped with minified JS, that was much more readable than this. Again, we know that this is a login application. We can just try to search for login. We also know like what message is being shown. Like if we try invalid some credentials, we know what message it will be showing. It shows this invalid credentials message, so we can just search for that. Yeah, and above that, we can see our username and password. So we can try to log in into the application using the same. So yeah, like these all things I had as a part of labs. After this, if you have any questions, I'll be happy to take them.